All right, so let's talk about AtwoodsMachine. AtwoodsMachine is a very simple machine. You basically have a pulley and you have masses attached by a string hanging over the pulley. I'm just going to make mass 2 equal to the mass that starts high up, and mass 1 the one that starts on the ground. Now mass 2 is going to be bigger than mass 1, so the gravitational pull will be greater on mass 2 than mass 1, and so mass 2 should fall, mass 1 should rise up. And so from this, we should be able to show that the total work is equal to the change in kinetic energy, or it's physics, so hopefully we'll get close. So first off, in terms of the total work, we need to do force diagrams. So for mass 2, we have two major forces acting on it. We have its weight acting down, and then we have a tension acting up. I'm going to call it FT2 for right now because of what I'm going to do next. Ultimately, it's one rope, and we're going to assume that the tension is constant throughout. So we're assuming that the string, or whatever it happens to be, is ideal. For mass 1, we have two major forces acting on it. We have its weight acting down, and then we have this FT1 acting up. And again, given the assumption that it's ideal, I know that FT1 equals FT2. So the total work will be the total work done by each, will be the sum of the works done by each of the forces. And so the total work, we have the work done by weight 2, we have the work done by tension 2, we have the work done by weight 1, and then we have the work done by tension 1. So we have work being done by all four forces. If you recall, work is equal to force times the displacement. And so if we look at this and think about dot product cares about how much of the force is in the direction of movement. So since mass 2 is going to fall, and we'll say a distance of h, mass 1 will also rise a distance of h. The string is not going to stretch anymore. It's not like mass 2 starts to fall while mass 1 hangs down on the ground. They will move together. They will move the exact same distance. Their displacements will be in opposite directions, though. Well, weight 2 is in the direction of the displacement of mass 2, and therefore it is positive work being done. And so it's just going to be the force weight 2 times h, or m2gh. The tension 2 is in the opposite direction of the displacement, so they are going to, it's going to create negative work, and so that's negative ft2 times h, which we can label as negative fth, since the tensions are the same, which we can go ahead and just say it's ft. The work done by weight 1 is going to be negative work because weight 1 is acting down, but mass 1 is going to be moving up. So the displacement's up, the force is down, they're in opposite directions, and so it's negative work. So we have negative weight 1h, or negative m1gh. And then the work done by tension 1, it is in the same direction as displacement. Therefore, the tension 1 and the displacement are both positive, are in the same direction. So the dot product, or the work, is positive. So this is ft2h, or ft1h, or fth. So now the total work is just the sum of these four works right here. And you would just add them up. They're scalars, you would just add them straight up. You don't have to worry about direction at this point. And notice that the work done by the tension cancels out, and what we're left with is the total work is just going to be m2gh minus m1gh. We can factor out the gh, so that's equal to m2 minus m1 times gh. All right, so that's the work being done. That should be equal to the total kinetic energy. So we'll squeeze that in over here. I'm assuming you have that force diagram already written down. So if we're claiming that the total work is equal to the change in kinetic energy, then we have m2 minus m1 gh is equal to k final minus k initial. Formula for kinetic energy you should know very well at this point. 1/2 mv final squared minus 1/2 mv initial squared is equal to m2 minus m1 gh. Now we're going to set up the system so that it starts at rest, so everything's starting at rest, and then you just sort of let go and they start to move because mass 2 will be bigger than mass 1. And so this velocity initial speed is 0 because it's 0 because the initial speed is 0 meters per second. And so what we're left with here is m2 minus m1 gh is equal to 1/2 this mass right here. Now this mass right there is the total mass that is moving. Technically the kinetic energy is the kinetic energy of mass 2 plus the kinetic energy of mass 1. They're moving at the same speed, so we can treat it as one object in a sense in terms of kinetic energy. And so this becomes 1/2 mass 1 plus mass 2 times Vf squared. And that is the relationship that we are going to check. And so we're going to set it up. I'm going to pause it in just a moment. I'm going to do this one more time just to show a different way of looking at the kinetic energy. So since kinetic energy is 1/2 mv squared, kinetic energy final, and if I have multiple masses in the system, this would be the kinetic energy of 1 plus the kinetic energy of 2 is the total kinetic energy. Kinetic energy of 1 is 1/2 m1v squared plus 1/2 m2v squared. They are moving at the exact same speed. The 1/2 is also constant to the two terms. In other words, I can factor out a 1/2 and a v squared, and I'm left with 1/2 m1 plus m2 v squared, which is what I had over there. All right, so I'm going to put it on pause. I'm going to set up the actual contraption, and we will tune right back in for that.